morning, everybody, and thank you for the organizers for inviting me here. It has been a really wonderful conference. So this is the contents of my talk. I will first advertise some other papers that I won't talk about, just in case somebody wants to discuss those with me in the coffee break or something. I don't know, it's strange to be so far. Yeah. And this is, yeah, maybe better be here. Yeah, then I will give some kind of a one-slide micro talks about our DMF T studies, 2 of them. And then finally I focus on the main topic, geometric origin of flat band superconductivity. And there I tell some stuff that I have told before, but I will tell something new that is not even in the archive yet. So, and here is the main message that's related to the new part. So if you don't remember anything else from this talk, this is what I would like you to remember, that we have considered the two-body problem of 2 attractively interacting particles in the flat band. And that already tells really surprisingly much about superconductivity in a flat band. Maybe it can even, give the essentials when you can have it. Okay, but these are these other works. So Tillman actually advertised this first one already, thank you. And then we have some other stuff. We have done a lot of work on FFLO, so if anybody is interested, including a review. And we have finally shown that the superfluid density is non-zero there. And then I have also experimental activity in the group. We have observed a new type of BC. But then let's go to this small talks about our DMF T study. So here we considered the very classic problem of doped, repulsively attractive Hubbard model. And you all know that there is a suggestion of D-wave superfluid at some parameter regimes. But there are also suggestions that this is competing with a stripe phase. So where the magnetization is modulated in space. And people have looked at both of those things with advanced methods, but we now looked both of them at the same time with cluster DMF T so that we can go beyond mean field. And we found that they can coexist. So this is as a function of doping the average magnetization. And this is the D-wave superconductivity parameter. And this is the wavelength of the stripes. And we can find regimes where they really coexist. And also in a kind of funny, unexpected way, that you would have the maximum of D-wave superfluidity and magnetization at the same position. Okay, so that's one. And then another work, yeah?
What lambda was it?
Lambda was, so these stripes are like a staggered magnetization. So that's the wavelength of that magnetization. So we plug it in as a parameter, and then we see what gives the minimum energy. Okay, then another DMF T work. Here we looked at Lib Lattice, which has a flat band. So I have this, I'm really fascinated about this flat band. So there, for instance, the normal state can be quite unusual. So we found that near the flat bands, one can find a non-magnetic and non-Fermi liquid metal normal state, plus some other more usual phases. Okay, so then I go to the main topic, and we have had a bunch of papers on this, and this is the new stuff. It's not yet published, but it will be in the archive very soon, depending on how much I manage to work on the flight back. So, basics. Now, periodic structures have, they fulfill the Bloch theorem. So you have eigenfunctions like this. This is the Bloch function. This is the periodic part of the Bloch function. And this is a very important quantity for my talk and also in general. So in this Percy band, you have some non-zero band with flat band means that, well, it's flat. Basically, the group velocity is 0. And the flat band, I don't mean it needs to be exactly flat just that if you're looking at interaction phenomena, the interaction is quite much bigger than the bandwidth. Then you will start to see maybe a flat band effect. Okay, a lot of interesting stuff happens in flat bands because obviously interactions dominate. Also, you may think that quantum fluctuations and disorder and those also would be stronger than usually. But I have been interested in pairing, and already the PCS theory gives a dramatic difference between dispersive band. This is the formula that you learn at school, and now if you do a PCS prediction for TC in a flat band, it actually becomes linearly dependent on the interaction times the volume of the flat band. So it's hugely different. And this can lead in principle to very high critical temperatures. So maybe a flat band would be the route eventually to room temperature superconductors, which I think we are all after in the end. This V flat band. This is the volume of the flat band. So it's just integrate all K momenta that you have there. Okay, but so this prediction has been there for a while, but we wanted to ask that is it actually a superfluid? Because your, let's say, naive picture of a flat band is that nothing moves because group velocity is 0. And actually, if you do the simplest theory of superfluid weight or superfluid density, it's 0 because of this thing. So we started to look at this question. And it turns out to be that these Bloch functions, these ones, are extremely important in this question. And you know that they are also related to topological quantities. So Berry curvature is basically given by derivatives of the Bloch function, and of course then the Z number when you integrate over Brillouin zone. So these things will come up. And here is again the main message of our investigations. So we can show that indeed there is superfluidity in a flat band, and that actually in general is connected to a quantity called quantum metric. And what's that? Well, this is what the name says. So these people wanted to make a definition for quantum metric in a sense that if you make an infinitesimal change in a parameter, how does your wave function change? So how far is the state when you make this small change? And then you can show that it looks like this. And this is actually not a cage invariant, so they did some further steps to make it cage invariant. And from that, they define this kind of tensor called quantum geometric tensor. And its real part is now the quantum metric, which is really just describing what is the infinitesimal distance in this submanifold of your Hilbert space. And then the imaginary part is Berry curvature. So there was a connection to these things in this object. And this quantum metric in some other communities is called the Fubini study metric, and it's also related to Fisher information. It's not exactly the same, but related. And this quantum metric is only emerging in physics, I would say. So there are these two siblings, the Berry curvature and the quantum metric parts of the same tensor. And you know, Berry curvature is already extremely famous and has been observed many contexts and so on. But the quantum metric, well, there is some theory work now in recent years, actually even in this decade, all of them. And what comes to experiments, it is sort of inside in these experiments, but has not been explicitly discussed. And now there is a first cold gas experiment where they have seen the Brillouin zone integrated quantum metric in Hamburg. So I think it's an interesting quantity to look at, and maybe we will learn a lot what is the significance of this quantity in physics. Then about flat bands. So why are they interesting? Well, I already said that all interaction effects and so on will be large, but also because you guys can create them. So one can have flat bands in lattices where you have a more complicated units and like Lib Lattice. This is from Professor Takahashi's papers. So for instance, in Lib Lattice, you can think that you can have a wave function where you have a plus sign here and minus sign here, and then they interfere and you will have nothing on the A side. So this is the basic mechanism of creating flat bands. Then you kind of block the movement by interference effects. Another way is to take some some systems where you have fluxes, because then you can have flat band basically by creating Landau levels. And then, of course, there is this recent discovery, I think in the sense of Tillman-Esslinger, of this magic angle bilayer graphene superconductivity, which we will hear more about tonight. And that's really interesting because the superconductivity appears when the Fermi level, when the Fermi level is at a flat band. So by changing some parameters, basically the angle, they can have different kind of band structures, and the superconductivity coincides with the flat band. So this, I think, is really exciting. And then I want to take this step-by-step approach to try to understand superconductivity in a flat band, starting from very, very basic things, like today I will show even the two-body calculations. Okay, but let's first see what we have seen from many-body calculations. So, by the way, so in order to answer whether there is superfluidity in a flat band, we calculate the superfluid weight. It's defined like this. It's basically the same as superfluid density, but now defined in a lattice context. So you can introduce a Coulomb per pair momentum in your Hamiltonian and calculate, for instance, the free energy change. And from there you get the superfluid density, and it should be positive and non-zero so that you can have supercurrent. So in other words, it's like seeing the stability of your system to a phase twist. There are also other ways of determining it, but this is the essential quantity. And you really need to have it non-zero to have the defining properties of superfluidity, because you could have large pairing, but still no superfluidity. This trivial example is an optical lattice with huge barriers between the sides. So you have a flat band, but that's a trivial one. You have only pairing, no superfluidity. Okay, so we go for this one. And we calculated first using multiband PCS theory. So all these systems where we can have interesting results, they must have multiple bands and attractive interactions, and we define order parameter, and then we calculate the superfluid density, and this is the essentials of the result. So the superfluid density will have a part that is the same as obtained earlier. It's the derivatives of the dispersion, and this is of course zero in a flat band. But there is another contribution that we call geometric, and this one can be non-zero in a flat band. So that's the essential one. And this is present only in multiband case. So in the usual single band Hubbard, for instance, is zero. And then when we look at closer this geometric part, we can get nice analytical result if we assume that the flat band is separated by other bands sufficiently, and so that the interaction is so small that you don't put particles on the other bands. And of course we have to have the flat band, so bandwidth smaller than the interaction. And then furthermore we assume uniform pairing, so that in all orbitals we have same pairing. And in this case, the results become very clear. So we recover this linear dependence on the coupling that was also obtained for the pairing gap. So it's the same comes for the superfluid density. And then this is filling, so there is some filling dependence, numbers of orbitals. And then this one now contains the quantum metric that I talked about, integrated over the Brillouin and so on. So this geometric quantity determines whether you can have superfluidity in a flat band. So as a reminder, this was this quantum metric, and you remember it had a connection to Berry curvature because it's part of the tensor whose imaginary part is Berry curvature, and then we can use that one and the positive semi-definiteness of this tensor to derive a lower bound for superfluid density. And this is that whenever you have either non-zero Chern number, or even if this is zero, if you just have non-zero Berry curvature somewhere in the band, then you are guaranteed to have superfluidity in the system. Okay, so that was based on mean field PCS theory in the multiband context. And of course, we want to, everybody asks, well, this is the mean field, how is the validity, especially in flat bands where the fluctuations can be large. So we have done a lot of further work. We showed the same results by perturbation theory, and then we compared the exact diagonalization DMF T and DMR T in certain model systems. So we have benchmarked this, at least in some cases, to more exact methods, and the result is the same. And we also did some semi-classical thing, so we pretty much believe it. And now I would like to discuss a bit what is the physics behind all this. So the essential things are overlap of the one-year functions, and that you must have a multiband process present. So in this picture, I have now a single flat band, meaning that the transport is zero. So that would be like a single band system. You don't have overlap of the one-year functions. And nothing moves. Okay, then if you have a multiband system with a flat band, you can have large overlap of the one-year functions, but particles don't move simply because of these interference effects of wave functions. Now when you add interactions, if you had this kind of trivial flat band, like a very deep optical lattice, you still don't see any transport. But now in the multiband system, because you have large overlap of the one-year functions, you get some kind of induced pair hopping, induced by interactions. And mathematically speaking, now it's easier maybe to understand the connection to the Chern number and so on, because it has been shown that if you have non-zero Chern number, then your one-year functions cannot be localized. So this somehow guarantees this overlap of one-year functions. These topological properties guarantee that, and that's needed. And then in this work where we derived the effective Hamiltonian, we could end up with this kind of spin Hamiltonian, where these are pair creations at different sites. And you can see that the pairs can hop if this is non-zero, this tunneling matrix element, and that turns out to be exactly this overlap between one-year functions. And this interaction-induced pair hopping has been predicted for bosons by Ehud and Sebastian Huber. And then I would also like to remind a paper by Leggett, where he looked at supersolids, and he also showed that somehow for this solid to be also super, you have to have always a density, so you cannot put the density to zero. Otherwise, you cannot establish a phase. So it's a bit similar to this. And then what about experiments? So what happens at high temperatures or finite temperatures? What were the things that you should look at? Well, basically, it's this linear scaling in U that is the essential thing. And most dramatic effects are for small values of U, like maybe like around 1 hopping or something. And here we have calculated the BKT temperature and BCS for the flat bands go like this. So this is the BKT and this is for dispersive band. And this zoomed up shows that especially for small interactions, these flat bands are dramatically better. And then for larger interactions, actually dispersive bands win. So this, of course, then makes one ask what happens above these critical temperatures. Do we know something about the normal state? And we have one study about that, where we looked at what happens in this type of Kreutz lattice when we put a flux in it. And I don't say much about this because I want to show the new stuff. But basically we showed that the carriers of current are always pairs, also in high temperatures. So one could see this kind of pair movement and localization of single particles also in the normal state. Okay, so now I go to this unpublished stuff. So I have all this explanation of the thing, but I was never very fully happy about the understanding that we have about this phenomenon. So I thought that, okay, let's look at the two-body problem in the same way as the Cooper problem was studied for superconductors by Cooper. And as a reminder, there you just look at two particles and add the Fermi C, which prevents scattering. And from that calculation, you actually get pretty much the features, basic features of PCS type of pairing, not quantitatively, but qualitatively. But you have to add the Fermi C. If you just solve the two-body problem in a dispersive band, it has nothing to do with superconductivity. You won't have a bound state. Okay, so now we have here the two-particle Schrödinger equation. So these now contain also the periodic potential, the lattice. And then there is interaction between the two particles. Lambda is the coefficient. And now in a flat band, we don't have a Fermi C. This is from the beginning very different from the Cooper problem. We don't have Fermi C. It's totally degenerate. And now what we claim is that we have to look at, of course, whether we have a bound state there, but not only whether there is bound state, but also whether this pair has a dispersion. Because single particles are hugely degenerate. And now if I create a pair, and if the pair is still degenerate, then it's very unlikely that I can create a superconductor because there is no preferred pair momentum where to go. But if the pair has a dispersion, then I can expect that there would be superfluidity, that the pair, there would be a minimum for momentum and you could sustain current, supercurrent. So let's look at this, and this is the solution. And here, this is the thing that is different now. This is a typical form for the scattering problem. But here at flat band, this is the flat band contribution, all energies are the same. So that's the different thing. And this can be solved, of course, exactly numerically, we have done it. But to obtain analytic solution, we take the isolated flat band approximation, so we neglect this one, and we use this separable potential approximation, which is often used and which is kind of okay for contact interaction. And this is the result. So this is now the binding energy. This should be negative to have a bound state. And okay, this is lambda. If you have attractive interaction, it's negative. Whenever this is non-zero. And the result is extremely simple. So this is the potential. And now x coordinate is like your orbital coordinate. We have a multiband system. The potential can depend on the orbital. And this is simply the overlap between the wave functions of the two particles that are scattering. So since there is no kinetic energy in the flat band, it doesn't appear. It's just the overlap. And now we can see about this Bayer dispersion finite effective mass by looking at this thing. So obviously there has to be some non-trivial dependence on Q. Q is the pair momentum in order to have this dispersion. So we expand this for a small q, and the result looks like this. So this is the binding energy, and you see here is q times q, so this is the inverse effective mass. It's written here. Effective mass is now given by derivatives of this kind of projector which just contains the Bloch functions. So these Bloch function derivatives will tell you whether there is a dispersion for the pair. And this result, by the way, this is a gauge invariant and basis invariant. It's very general, even when there are approximations. And then if we further assume that this pairing potential would be independent of orbital, so this kind of uniform pairing, then we get the same result as from the PCS mean field theory. So that this effective mass is proportional to quantum metric. And so this superfluid density, it has, of course, you can define it's like the inverse of the effective mass. So we really get the same result as from multiband PCS theory. And this multiband PCS theory we had in some cases mapped to exact results. So this is quite interesting. It seems that the essentials of this flat band pairing can come out from the two-body problem, which I think is quite nice in various ways. First of all, if you have a very, very complicated system like bilayer graphene, so you might actually start to study the two-body problem in full detail to see what is going on, and also in the search of new superconductors. And then also, if it's mostly two-body physics, then maybe it's a robust effect, and one can indeed have these high temperatures. Of course, I mean, one has to then compare what comes up with quantum fluctuations. And maybe the other way around, like if we find a finite effective mass, then yeah, you can expect superfluidity. On the other hand, if we don't, this would also maybe be some very exotic many-body state then, because it's highly degenerate for the pairs. Then we looked at a couple of model systems that you could do in your lattices if you are bored with the square lattice. So for instance, this sawtooth ladder, this is the band structure. There is one flat band, and nicely it's the lowest one. And now the exact two-body problem gives you this kind of binding energies, and this analytical formula that I showed gives this one. So because there is this separable potential approximation, it actually gives only one bound state instead of all, and that's why it's a bit off. But the dispersion is, I mean, the effective mass you can still got correctly, so it's quite nice. So for this system, yeah, you have this pair dispersion. And then for the Lib lattice as well, it works very well. This is the exact, and this is the analytical results. And here you can again see that there is pair dispersion. And I think I have 2 minutes or what? Yes. So I can propose an experiment for you, because maybe you want to explore other lattices than the square one, and this doesn't require extremely low temperatures. And things would be quite different from what you have seen so far. So there are many experiments where people look at, these are just two of many others, where people can monitor how things expand in a lattice. So I think this might be one of the easiest way of seeing these effects. So first, you would need to create a flat band lattice and put some kind of initial state there. And you could start with the dilute gas to just probe the two-body physics and later add more. And yeah, you have the initial state with some kind of initial trap or whatever. And then you see the expansion. And now this would be very different from many experiments that have been done, namely the non-interacting fermions or bosons, the two-body physics you can do with bosons, they should not propagate. So if you really have a flat band, they should be stuck. And then you put interactions, and then you should see propagation. Usually when you put on interactions, you have this t squared over u type of slower propagation. Now it should be much faster than in the non-interacting case, and it should be proportional to the interaction. So you tune that knob and it should go faster. And also it depends on these Bloch function derivatives. So if you change the type of lattice, it should be different. And yeah, for temperatures, the scales would be basically the scale of hopping. That's typically the band gap scale. U should be lower of the order of hopping, and then the temperature may be quarter of the hopping or something. Doesn't need to be like 1% or something. And that's my conclusion. So we have shown that the superfluidity in a flat band is possible. It's guaranteed by topological and geometrical quantities, and the two-body problem already seems to give much of the essentials of this phenomenon. And here are the people in particular, well, our ETH collaborators, Sebastian Huber on some of the parts, and then Sebastiano Peotta and Long Lian are the two very important postdocs in this work. Both are searching for positions if you are interested. Thank you.
An expression for the superfluid density as a function of filling,
yeah.
where it vanished at the nu equals 1 and nu equals 0.
Yes.
So in quantum Monte Carlo simulations of the attractive Hubbard model on in Lib Lattice, you see a minimum of the pair structure factor at those fillings because of a competition with charge density wave formation. Is that why your d sub s is vanishing there also, or is it just low filling?
It's just more like low filling, because this is PCS theory. It doesn't take into account this competition with the charge wave. Yeah, no.
Maybe I had two questions. One is, at the end of your talk, you said if you have a flat band and you have non-interacting particles, they would not expand because
yeah.
the group velocity is 0. But if you have then interactions, because now I want to really understand it, the pairs have now dispersion, that's why they expand.
Yeah.
Should I now regard at the expansion in the interacting system as an expansion of pairs or of single atoms? And then if it is an expansion of pairs, an effective velocity is always you hop one lattice constant in a tunneling time. Is the tunneling time for the pairs now a super exchange time j square over u?
Yeah, so to answer first question, yes, it would be movement of the pairs and single particles. It's funny, at least in some systems that we have studied, the single particles really would stay stuck also in a case of interaction. So if you have an imbalanced system, only the pairs would propagate and the single extra particles would get stuck. And then, yeah, this is the whole thing. This velocity of the pairs or effective mass, it has now nothing to do with this t squared over u. It's not a super exchange process. So it's linearly proportional to u, linearly proportional to the coupling. And then it depends on some properties of the Bloch functions of the multiband system. So it would be very different velocity. So it's like an interaction-induced hopping. So it's not a super exchange process.
Is there a simple model for that? Or?
I think the simple way to understand, but the simple way to understand it is that we have the localized states take a basis of localized one-year orbitals in the flat band, right? And they're orthogonal one-year orbitals. Since they overlap spatially, there is interaction between them. So the interaction has kind of 4 particles. Once you apply the interaction within that space, basically generates pair hopping, right? So you have no kinetic energy. You just have a basis of states that are not completely local. They're local over.
Yeah. So
And if you just apply the
localized
interaction,
spaces,
right.
but you are delocalized.
yeah. The one-year functions are never localized. They are always overlapping with the neighboring sites. So you cannot, in a way, to think that your particle is in one site only, because the one-year functions are delocalized.
My second question is, what really depends on the presence of multibands? Because you can have a single band which is a flat band. I don't know, your two-body problem was probably solved in the single flat band. But if,
Yeah.
the curvature and those things come in, this is usually only present if you have a multiband
Yeah.
and you eliminate, the higher bands adiabatically. So what
Yeah.
part of you said in terms of pairing and pair propagation requires multiband, or what would also happen in a single band?
So everything requires multiband. So if I have just a trivial single band system like the single band Hubbard model, I would not see this at all. But there is a thing, when I say here that I neglect explicitly this other band's contribution, that means that I focus on the physics of the flat band, but the existence of having many bands is now encoded in the Bloch functions. So the Bloch functions are calculated for the whole system, and that I have to do exactly by including all bands.
It's also related, I think, to what I said before, that if you have only a single band and you have localized one-year orbitals, they would have to be localized on one side.
Yeah.
And then the interaction would not do anything.
Yeah.
Unless it's not local.
Yeah.
If it's not local interaction, you already made it anyway. Good. It's only a local interaction.
Local interaction.
There is one question.
Yes. So I wonder when you say multiband, it's like only one band is flat band, others are not. Is that correct? Or all the bands are flat band?
Well, this doesn't really. Yeah. Question was, does it matter whether all the bands or one band are flat and so on? It doesn't really matter. I always focus on the physics that happens in one flat band, but then there are many other, and those can be either dispersive or flat.
So I'm not sure whether I understand this correctly. So it's like the effect of multibands is you kind of create overlap between one-year functions on different lattice size.
Yes.
And it is the interaction that can coupling this one-year states on different sides.
Yeah.
Correct?
Yeah. That's
So
correct.
necessary to have
Yeah. So the multiband nature is essential for creating this overlapping one-year function, and then with interactions, hopping can be induced.
Well, I just wanted to know, is there any, is it sensible to think about the symmetry of the paired wave function, like you do in PCS theory?
Which symmetry?
Symmetry.
Yeah.
So like orbital symmetry, S wave, P wave, pairing. I mean, is it sensible to think of in those terms, or is it you have to think in a different way?
Well, I think, we have so far looked at S-wave pairing. In one paper, we extended a bit, so these concepts don't get killed if you go to other types of pairings. And of course, in the two-body problem, this was assumed attractive interaction and contact interaction, the simplest case. But there one could easily extend it to some kind of effective attractive interaction between nearest sites, and that would be like the D-wave pairing or something.
And I guess this condition of Cooper pairing still holds that
you'll get pairing for arbitrarily small lambdas, right?
Yeah, yeah.